Today we'll discuss CMI's 2021 paper, and the first question is, we are given two equations and we have to find number of solutions of these two equations. Now the first equation is log a base 2021 equals 2022 minus a. Now clearly a is greater than 0. Now if we write a function fa, we can write this function fa as log a base 2021 plus a minus 2022. If we differentiate this, we'll get 1 upon a log 2021 and plus 1, which is greater than 0. That means this function, it is strictly increasing. Now we look at f0 positive. So at 0, we have this log 0, and log 0 tends to minus infinite. And if we take this limit, a tends to infinite, log infinite is infinite, this is also infinite. So this function, it is strictly increasing. It starts from minus infinite and it goes all the way up to plus infinite. So this function, it will intersect x-axis exactly at 1 point. So there is exactly one solution to this equation. And from inspection, we can clearly say that this one solution is when the value of a is 2021. Now, if we look at the second equation, we can write this function as sum GB and LB 2021B plus B minus 2022. Now again, G dash B LB 2021 to the power B into log 2021 plus 1, which again is greater than 0. So again, this function GB, it is an increasing function. Now when B tends to minus infinite, this is 0 and it approaches minus infinite, and at plus infinite, this is infinite and this is infinite. So this function gx, it also approaches infinite. So this function also, it is an increasing function and it starts from minus infinite and it reaches plus infinite. So it will intersect x-axis exactly once. So this second equation also will have exactly one solution. And from inspection, we can say that one solution is when the value of b is 1. So we have unique solution for both the equations. And the first case, value of a, it must be 2021, and value of b, it must be 1. So the correct options are equation 1 has a unique solution, equation 2 has a unique solution, and a equals b, it is not possible. And there exists a solution a for 1 and solution b for 2 such that a plus b is an integer. So the correct options are a, b and d. Now the second question is a prime p which is greater than or equal to 2 whose only positive integral factors are 1 and p. Now the first one is for any prime p, the number p square minus p is always divisible by 2. Now if we look at p square minus p, it is p into p minus 1. Now since it has to be true for any p which is greater than or equal to 2, if we choose p as 2, we'll get p square minus p as 2, which is not divisible by 3. So it is not true for all the primes. So option A, it is incorrect. Now it says for any prime p greater than 3, exactly one of p minus 1 or p plus 1 is divisible by 6. Now if we look at three consecutive numbers, p minus 1, p and p plus 1, exactly one of them will be divisible by 3. Now since p is prime, it cannot be divisible by 3. Now p minus 1, it is even, and p plus 1, it is even since p is odd prime. So out of these two, p minus 1 and p plus 1, exactly one of them is divisible by 3 and both of them, they are divisible by 2. So exactly one of them is divisible by 6. So this option B, it is correct. Now if we look at p square minus 1, we can write this p square minus 1 as p plus 1 into p minus 1. Now in the previous part, we have already proved that out of these two, one of them, it is exactly divisible by 3. And since both are even numbers, one of them, it must be of the form 2k and the other one, it must be of the form 4k. So it is divisible by 8. So once it is divisible by 8 and 3, it will be divisible by 24. So this option C is also correct. Now the next one, for any prime p greater than 3, one of the three numbers, p plus 1, p plus 3 and p plus 5, it is divisible by 8. Now if we take this p as p congruent 1 modulo 8, then p plus 1 will leave the remainder 2, p plus 3 will leave the remainder 4 and p plus 5 will leave the remainder 6. So neither of p plus 1, p plus 3 and p plus 5 is divisible by 8. So this option D, it is incorrect. So the correct options are B and C. Now here the question is, we want to construct a triangle ABC such that angle A is 20.21 degrees and side AB has length 1. So we have side length AB of length 1 unit and then this angle is 20.21 degrees. So we have this angle A which is 20.21 degrees. Now length of side BC is X. Then we have to find number of triangles depending on the value of X. Now what we'll do is we'll find perpendicular distance from B to this side, and this distance will be equal to 1 sine 20.21 degrees. So this distance, it is sine 20.21 degrees. If we take X smaller than D, in that case this arc from B, it will never intersect this line. So in this case, number of triangles possible will be simply 0. Now if we take this X as D, then it will just touch this line, and in that case we'll have just one triangle. Now if we take this X greater than D but less than 1, in that case if we draw this arc, it will have 2 points of intersection. Then we'll have this ambiguous case where we have two different triangles. So in this case, value of nx will be 2, and if x is greater than 1, in that case again it is going to intersect only once. So this nx in that case will be simply 1. So the possible values of nx are 0, 1 and 2, and which gives us options A, B and C. So the correct options are A, B, C. Now here the question is, consider a polynomial of the form x cube plus ax square plus bx plus c, where a, b, c are integers. Name 3 possibly non-real roots of fxb, p, q and r. Now the first one is, if f1 equals 2021, then fx is x minus 1 into x square plus sx plus t plus 2021, where s and t must be integer. Now this is nothing but this is remainder theorem. If fx is divided by 1, it leaves the remainder 2021, and since leading coefficient is 1, so we can express this fx as x minus 1 into this quadratic expression x square plus sx plus t plus remainder 2021. So this option A, it is correct. Now the second one is, there is such a polynomial fx with c equals 2021 and p equals 2. Now this p equals 2 is a rational root, and rational root theorem says this p, it must be a factor of plus minus c by a. Now in this case, plus minus c by a is plus minus 2021, which is an odd number, and this p, it is an even number. So it is not possible to have a root whose value is 2. So this option B, it is incorrect. Now the next one is, there is such a polynomial fx with r equals 1 by 2. Now this r, it again is a root of this function fx. It is also a rational root. Now if it is a rational root, then we get this root from this expression plus minus c upon 1. Now c is an integer and there is this 1 in the denominator. So we cannot have r as 1 by 2. So again, this option C is not possible. Now for this option D, we can write p square plus q square plus r square as p plus q plus r whole square minus 2pq plus qr plus rp. Now p plus q plus r, this is minus a, so it will be a square and then minus, and this is s2, which is b. So this p square plus q square plus r square, it doesn't depend on c. So this option D is also correct. So the correct options are A and D. Now question number 5 is, for any complex number z, we have defined a function pz, which is cardinality of z to the power k, where k is a positive integer, that is number of distinct positive integral powers of z. Now it may be useful to remember that pi is an irrational number. Now the first one is, for each positive integer n, there is a complex number z such that pz equals n. Now if we take this z as nth root of unity, which is e to the power iota 2r pi by n, then any z to the power k will be of the form 1 alpha alpha square and alpha to the power n minus 1. So every power of z to the power k, it will belong to this set having n elements. So that means this option A, it is correct for any z which is nth root of unity. Now the next one is, there is a unique complex number such that pz equals 3. Now again for this, what we'll do is we'll take third root of unity, and which are 1, omega and omega square. Now if we take z as omega, we'll have 3 roots, and if we take z as omega square, again we'll have this cardinality as 3. So that means this option B, it is incorrect. If mod of z is unequal to 1, then pz is infinite. Now if mod of z is unequal to 1, we can write this z as r into e to the power iota theta, where r, it is unequal to 1. We can write z to the power k as r to the power k into e to the power iota k theta. Now this complex function is a multivariate function. Every time we rotate it by some angle, it also changes its magnitude. So this z to the power k, it can never come to any previous form. So in this case, number of solutions, they'll be infinite. So that means this option C is incorrect. And this option D is p e to the power iota. Now p e to the power iota will be e to the power iota k. Now this e to the power iota k, it will have this unit circle and it will have infinite points. So for these infinite points, we'll have infinite cardinality. So option D is also correct. So the correct options are A, C and D. Now the question is, a stationary point of function is a real number r such that f dash r is equal to 0. A polynomial need not have a stationary point. Consider a polynomial px. If px is of degree 2022, then px must have at least one stationary point. Now for this polynomial px, if we write p dash x is a polynomial of degree 2021, which is odd, and any odd degree polynomial will have at least one real root. So it must have at least one stationary point, and that means this option A, it is correct. Now this B is, if the number of distinct real roots of px is 2021, then px must have at least 2020 stationary points. Now one of the implication of Rolle's theorem is, in between any two roots alpha 1 and alpha 2 of continuously differentiable function, there exists at least one point at which p dash x is equal to 0. Now we consider these 2021 roots, then we'll have 2020 pairs of roots, and in each pair there'll be at least one root of p dash x. So that means it'll have at least 2020 stationary points. So that means this option B is also correct. Now if we look at this option C, if the number of distinct real roots of px is 2021, then px can have at most 2020 stationary points. Now this is not true. In between any two roots, say alpha 1 and alpha 2, Rolle's theorem says there will be at least one root, but then it is possible to have more than one roots in between any two roots of px. So this option C, it is definitely incorrect. Now the next one is, if r is stationary point of px and second derivative is 0, then this point is neither a local maxima nor a local minima. Now this is not true. So if second derivative is 0, that doesn't mean it is a point of inflection. It simply means that the second derivative test fails and we have to check it using either nth derivative test or first derivative test to ascertain whether it is a maxima or a minima or a point of inflection. So it is not true for all the cases. So this option D is also incorrect. So the correct options are A and B. Now question number 7 is, we are given three distinct positive constants A, B and C, and we want to solve the simultaneous equations ax plus by equals root 3 and bx plus cy equals root 3. Now both these equations, they represent straight lines. Now first is, there exists a combination of values of A, B and C such that the above system has infinitely many solutions. Now we know that two lines, they'll have infinite solutions if they are same lines. So in that case, we'll have A1 upon A2 equals B1 upon B2 equals C1 upon C2. So for this, we'll have this condition A upon B must be equal to B upon C, and it must be equal to root 2 upon root 3. So it is possible to have this combination. Say for example, if we take A as root 2 by root 3, B as 1 and C as root 3 by root 2, it satisfies this condition. So it is possible to have positive values for A, B and C such that the system of equation has infinitely many solutions. Now the second one is there exists a combination of values of A, B, C such that the above system has exactly one solution. Now if it has exactly one solution, then they must not be parallel. In that case, A upon B must not be equal to B upon C. So if B square, it is unequal to AC, in that case, it will always have one solution. So this option B, it is correct. Now for no solution, these two lines, they must be parallel and they must not be same. So in that case, we'll have A upon B, it must be equal to B upon C, but it should not be equal to root 2 upon root 3. And in this case, we'll have B square equals AC, that is B is geometric mean of A and C. Now, if we take its arithmetic mean, A plus C by 2, we know that arithmetic mean, it is always greater than its geometric mean, which is B. So from here, we get this condition that 2B is less than A plus C. So this system of equation will have no solution, then 2B should be less than A plus C. So this option C is also correct. Now for this option D, it says if 2B is less than A plus C, then the system has no solution. Now this is not true. If we take any B, which is B square is unequal to AC, in that case, it will always have a unique solution. So this option D is incorrect. So the correct options are A, B and C. Now question number 8 is, we are given two distinct non-zero vectors V1 and V2 in 3 dimensions. Define a sequence of vectors by Vn plus 2, which is cross product of Vn and Vn plus 1. Now this set S is the set of Vn and this U is set of unit vectors. Now the first one is, there exists vectors V1 and V2 for which cardinality of set is 2. Now we have two non-zero vectors V1 and V2, and if we take their cross product, then we'll always have this third vector which is different from V1 and V2. So we cannot have cardinality of S is 2. So this option A is incorrect. Now the next one is, there exist vectors V1 and V2 for which cardinality of S is 3. Now we know that I, J and K, they form a reciprocal system of vectors. So we know that I cross J is K, J cross K is I, and then K cross I is J. So we'll keep getting these three vectors I, J and K from I, J, K. So it is possible to have cardinality of the set S as 3. So this option B, it is correct. Now the next one is, there exists vector V1 and V2 for which cardinality is 4. Now for this case also, we'll use this fact. So what we'll do is, rather than taking them as I, J and K, we'll take these vectors as some combination, say I plus J and then J and K. Now this is your V1 and suppose this is V2. Now V1 cross V2 is I cross J plus J cross J. J cross J is 0. So we'll get this as K. V2 cross V3 will be J cross K I, and then it'll be J. So now we have I plus J, J, K and I. We have 4 different vectors. So in this case, cardinality of this set is 4. So this option C is also correct. Now this D is, now suppose for some vectors V1 and V2, the set S is infinite, then the set U is also infinite. Now this is not necessarily true. So for this, what we'll do is, rather than taking them as I, J and K, we'll take them as, suppose 2I, 2J and 2K. Now if we multiply them, we'll get 4I cross J and there'll be 4K and then it'll be 8I. So every time this magnitude is going to change. So we have infinite vectors which are parallel to these 3 vectors I, J and K. But in this case, the set U, it will only have 3 elements I, J and K. So that means this option D is incorrect. So the correct options are B and C. Now question number 9 is, we need to find these limits. Now for this function fx, if we take this limit x tends to 0, x upon x plus sin x, now we can write this as 1 upon 1 plus sin x upon x. Now sin x upon x is 1, so this value is 1 by 2, so this option A is correct. Now if we take this limit x tends to infinite, in that case we can write this as limit x tends to infinite. This is 1 upon 1 plus sin x upon x. Now this is oscillating value minus 1 to 1 upon infinite, so it will be 0. So in this case, value of this limit is 1. So this limit, it exists, so this option B is incorrect. If we take this limit x tends to infinite, we can write limit x tends to infinite, x to the power 4 plus x to the power 6 upon e to the power x minus 1 minus x square, infinity upon infinity form. Now if we keep using L'Hopital's rule, then we can write this as limit x tends to infinite. It will be factorial 6 upon e to the power x. Now e to the power infinite is infinite. So anything finite upon finite will be 0. So this limit x tends to infinite, gx is finite. So this option C is also correct. Now we look at this option D, limit x tends to 0, gx. Now we use L'Hopital's rule in this. We can write limit x tends to 0. Now this is 4x cube plus 6x to the power 5. Now this is e to the power x minus 2x. Now this limit, it is 0. So this option D, it is incorrect. So the correct options are A and C. Now this 10th question, we are given this tan inverse function in its principal value range, which is from minus pi by 2 to plus pi by 2 not inclusive. And then GV is 0 to V ft dt. Now the first one is F1 is pi by 4. Now F1 is tan inverse 1 and tan inverse 1 is pi by 4 in principal value range. So this option A, it is correct. Now this option B is tan inverse 1 plus tan inverse 2 plus tan inverse 3. Now if we use tan inverse x plus tan inverse y, it will be tan inverse 1. Now in this case, x into y is greater than 1. So it will be pi plus, now it will be tan inverse x plus y upon 1 minus xy. So it will be tan inverse minus 1. So it will cancel. So this value will be equal to pi. So this option B is also correct. Now it says gx is an increasing function. So if we find g dash v will be fv and fv is tan inverse v. Now this tan inverse v, it is positive as well as negative. So whenever v is less than 0, this value is negative. So this function g, it is not an increasing function for all the values of v. So this option C, it is incorrect. Now this D is, g is an odd function. Now if we look at g dash v is equal to fv and fv is odd. Now if g dash is odd, it simply means gv, it is an even function. So this option D is also incorrect. So the correct options are only A and B.